You are witnessing ambition meeting physical limits. Octagon is the largest floating structure ever engineered, stretching 7 kilometers across the Red Sea. As part of the $500 billion NEOM project, Octagon is an industrial hub where semiconductor manufacturing is executed directly on the water. The central question is, how do we build stable foundations for precision semiconductor plants on a surface that is constantly in motion? The answer lies in hollow modules. We use high-strength concrete and anti-corrosion alloy steel to create stable, positive buoyancy for the city. The process begins by casting octagonal modules in dry docks, each designed with a honeycomb structure to optimize structural stress and stability. The dynamic positioning DP3 system is the core technology used to keep the entire 7-kilometer structure from shifting more than 1 centimeter. 32 azipod thrusters, each with 20 megawatts of power, constantly adjust force vectors based on real-time satellite and flow sensor data. The real challenge is the sophistication. Observe the multi-stage air filtration line specifically designed for the harsh and salty maritime environment. Sea salt is the enemy of silicon. We deploy electrostatic filtration with ULPA membranes, removing 99.9997% of dust particles as small as 10 nanometers. This process consumes 1.5 gigawatts of power, fully supplied by offshore floating wind farms and double-sided solar panels covering the western surface. At the center, we establish zero vibration zones. Here, ASML EUV lithography machines are placed inside 2-meter thick steel protective pods for absolute stability. Foundation flatness is controlled within less than 0.5 millimeters per kilometer, an unthinkable feat for traditional maritime engineering and structural design. The assembly requires 5,000-ton gantry cranes operating in sync with laser guidance systems to join the massive modules beneath the water's surface. Underwater welds are performed by survey robots using high-pressure laser technology to ensure absolute airtightness for at least 50 years of operation. This is only the foundation. Next, I will lead you deep inside the chip production line, where we effectively defy the laws of thermodynamics. Environmental control begins with air. We operate the largest atmospheric filtration system ever integrated into a floating industrial complex for maximum purity. Massive 30-meter towers inhale Red Sea air, processing 100 million cubic meters daily to strip away every trace of corrosive salt. Primary filtration stages eliminate salt crystals larger than 10 microns to prevent electrochemical corrosion on the sensitive semiconductor fabrication equipment. Air is channeled through cold traps to condense moisture, maintaining a relative humidity of precisely 45% with extremely tight tolerances. Maintenance robots on overhead rails constantly replace saturated HEPA filters using precision vacuum-sealed robotic manipulators in a perfectly synchronized sequence. The system provides ISO Class 1 air for wafer fabrication, a sterile environment where a single dust particle can destroy thousands of chips. Inside the lithography chamber, ASML extreme ultraviolet machines operate within a vacuum environment that is purer than the vacuum of deep space. Fabricating 2-nanometer chips requires nanometric precision. Our EUV system uses a 30-megawatt laser to generate plasma and 13.5-nanometer light waves. This light beam is focused through complex optics, with mirror flatness controlled at molecular levels before being projected onto the silicon wafer. Observe the EUV robotic arms moving wafers with 8G acceleration, running 24/7 to ensure maximum global semiconductor output and efficiency. The heart of the line lies in printing billions of transistors onto an area smaller than a fingernail, defying traditional limits of optical physics. Wafers undergo 1,000 complex process steps, from photoresist coating and ultraviolet exposure to chemical acid etching and high-energy ion implantation. Autonomous underwater drones inspect Octagon's submerged structural integrity, ensuring maximum stability for the zero vibration zones located above the surface. Submerged weld inspection is performed using multi-angle ultrasonic technology, detecting every microscopic air bubble within the high-strength lightweight concrete modules. You are witnessing the convergence of maritime engineering and nanotechnology. Next, we activate magnetic levitation buffers to eliminate all oceanic vibrations.
Welcome to Octagon. We are here at the Red Sea Industrial Hub to see how this futuristic development is integrating with the natural environment.
Red Sea waves reach heights of 1 meter, but EUV lithography machines demand stability down to a small fraction of a single nanometer. The technical solution is our active magnetic levitation system, creating a physical disconnection between the manufacturing floor and the floating hull. Ultra-sensitive laser interferometers and accelerometers measure foundation oscillation, transmitting billions of data points to the central processing unit in real time. This data feeds thousands of electromagnetic actuators beneath the deck, generating an instantaneous and precise counterforce to cancel out all external motion. Consequently, the lithography floor effectively floats in midair, held by magnetic fields and isolated from the turbulent maritime environment outside. Observe the installation of 2-meter-thick steel protective pods. Every single weld undergoes rigorous X-ray stress testing to ensure an absolute vacuum seal. I will guide you through the logistics of transporting a $200 million ASML machine from the dry dock to its offshore operating position. We utilize dynamic positioning barges and heavy-lift gantry cranes, working in perfect synchronization with laser guidance beacons for extreme placement accuracy. Positioning tolerance during final placement is kept under 0.5 millimeters, monitored by high-precision underwater survey robots throughout the entire process. To power this complex, we deployed double-sided solar panels and offshore wind turbines integrated directly into the Octagon's massive perimeter. Assembling these 12 artificial islands into one 7-kilometer structure is a monumental feat of modular engineering and subsurface docking technology. Each azipod thruster uses 20 megawatts of power, continuously adjusting the hull's vector to counteract powerful currents and tidal forces. We embedded over 10,000 sensors throughout the structure to monitor thermal expansion and mechanical stress caused by the harsh saline atmosphere. All data is analyzed by the Dark Machine AI to predict and prevent structural fatigue long before it impacts advanced semiconductor production. The quality control phase is a brutal gauntlet. We execute acoustic shockwave tests to simulate the impact of Category 5 hurricanes. Real-time X-ray systems scan 100% of submerged structural welds, searching for microscopic air bubbles within the high-strength lightweight concrete modules. Observe the kinetic impact stress test, where we simulate a direct collision with a massive, ultra-large crude carrier vessel at sea. Data from thousands of pressure sensors is analyzed instantly to evaluate material fatigue of the octagonal modules under extreme mechanical loading. Any module failing these rigorous stress tests is immediately replaced by 5,000-ton robotic cranes to maintain zero-defect structural integrity. Specialized underwater autonomous vehicles inspect the deep-sea concrete foundations, ensuring a continuous 50-year operational lifespan for the entire city. Observe our senior engineers operating the DP3 positioning system, constantly neutralizing the hull's movement against the powerful Red Sea currents. The activation of active magnetic levitation buffers is complete, achieving nanometric stability for our extreme ultraviolet lithography machines despite the waves. This is the final verification stage. We are conducting a comprehensive system-wide stress test to ensure total operational synchronization before mass production. Observe the EUV robotic arms accelerating silicon wafers at 8G, requiring an absolute vacuum and vibration-free environment to succeed. 10,000 independent sensors measure every micro-oscillation of the Octagon foundation in real time, allowing for immediate and precise stabilization corrections. In the post-lithography wafer processing unit, every single wafer is subjected to a final high-frequency ultrasonic stress test for potential defects. You are witnessing the quality verification of the first 2-nanometer chips manufactured entirely within a floating oceanic industrial complex. This process represents the fusion of brutal maritime engineering and the most sophisticated nanometer technology ever conceived by the human mind. The testing and stress validation phase is officially concluded. We are now ready to activate Octagon as the world's largest automated production hub. The logistics of supplying a floating plant are staggering. We have engineered an automated maritime shuttle system to transport raw silicon wafers daily. These autonomous vessels utilize AI-driven navigation to dock with Octagon's internal port, maintaining stability even during heavy 5-meter sea swells. Inside the facility, levitating maglev conveyors move materials at high speeds, completely eliminating mechanical friction and potential dust contamination. Every single movement is synchronized by the central neural network, ensuring that the supply chain never stops for even a fraction of a second. Observe the power distribution core. To sustain the EUV machines, we manage a localized power grid handling 1.5 gigawatts of energy. The heat generated is immense. We utilize a closed-loop deep-sea cooling system that exchanges thermal energy with cold Red Sea currents. Titanium heat exchangers with anti-biofouling coatings ensure maximum efficiency while resisting the aggressive corrosion of the high-salinity maritime environment. In the event of a power fluctuation, the facility switches to its massive graphene supercapacitor banks instantly to maintain operation. These banks provide full operational power for 30 minutes, allowing for a controlled shutdown or transition to backup hydrogen fuel cell generators. Hydrogen is produced on-site through massive electrolysis units, using excess renewable energy harvested from our floating wind and solar arrays. Observe the precision of the robotic arms in the chemical vapor deposition unit. They operate with a combined accuracy of 0.1 nanometers. Each semiconductor layer is inspected by high-energy electron microscopes before moving to the next stage of the 12,000-step manufacturing sequence. We are not just manufacturing chips, we are perfecting industrial autonomy on a scale never before attempted on the open ocean. Structural integrity of the clean rooms is monitored by internal atmospheric sensors, detecting any chemical imbalance or pressure drop within milliseconds. This represents the pinnacle of human engineering. Every component, sensor, and machine works in a symphony of perfect industrial logic. Octagon's efficiency relies on an automated logistics spine. We integrated a high-speed underground maglev network to transport components through the facility. This system moves raw materials from the port to the clean rooms in under 3 minutes, completely bypassing the external maritime environment. Observe the heavy-duty robotic sorters. They utilize multispectral cameras to identify and organize thousands of hardware parts with a 0% error rate. To maintain extreme precision, we must control the thermal output of the entire 1.5 gigawatt power distribution core effectively. We engineered a revolutionary closed-loop cooling system that pulls cold deep-sea water from a depth of 400 meters below the Octagon. Water passes through giant titanium heat exchangers, absorbing immense thermal energy generated by EUV machines and massive server arrays. Used water is treated and released back into the sea at a regulated temperature to prevent any localized ecological thermal impact. In the hydrogen production sector, we utilize excess energy from the offshore wind farm to power high-capacity industrial electrolysis units. Green hydrogen is stored in double-walled carbon fiber tanks, serving as a clean fuel source for Octagon's heavy transport fleet. Structural drones patrolling the perimeter use high-resolution thermal imaging to detect any micro-fissures caused by saltwater corrosion. Each drone is equipped with a repair module capable of applying military-grade anti-corrosion sealant to any identified structural weakness immediately. Semiconductor module assembly is performed by an army of robotic arms operating within a nitrogen-purged and hyper-sterile environment. These robots utilize advanced haptic feedback sensors to handle delicate silicon wafers with a force precision of less than 0.1 newtons. This is the culmination of industrial autonomy. No human intervention is required for the primary fabrication and packaging of these 2 nanometers chips. The entire facility operates as a single living organism, optimized by the Dark Machine AI to achieve maximum output and zero waste. We are entering the most critical phase of assembly. This is where theory meets the brutal reality of the open sea. Installing the main optical lens into the EUV vacuum chamber requires a precision tolerance of less than 0.1 nanometers. A single grain of salt or microscopic vibration during this 8-hour procedure would result in the total loss of the entire system. To prevent this, we activate the gigafilter sequence, creating a hyper-clean environment with internal pressure higher than the exterior atmosphere. Robotic manipulators lower the 500-kilogram silicon carbide mirror, using laser interferometry to guide every single micron of movement. Simultaneously, the active magnetic levitation system is pushed to its limit, neutralizing the impact of an approaching 3-meter ocean swell. The cooling manifold circulates liquid nitrogen at -196 degrees Celsius to stabilize the laser generator's thermal expansion. The 12 independent octagonal modules are now locked into a unified structural grid via high-power electromagnetic coupling. The power core is ramped up to 1.5 gigawatts. You can see the plasma ignition sequence beginning inside the EUV source chamber. Massive superconducting magnets are energized to shape molten tin droplets, preparing them for the 30 megawatt CO2 laser impact. This is the make or break moment. If the laser to droplet alignment is off by even 1 micron, the entire plasma generation sequence will fail. Success. The first 13.5 nanometer ultraviolet light beam is generated. We have achieved stable lithography on a floating platform. Automated quality control scanners are verifying the circuit patterns on the first production-grade 2 nanometer wafer ever manufactured at sea. Notice the zero vibration reading on the console. Our engineering solution has officially conquered the kinetic energy of the Red Sea. The production cycle is now continuous. Octagon is no longer a construction site. It is a fully operational, molecular-scale factory. To maintain thermal equilibrium, we engineered a massive deep-sea cooling lung located directly under the Octagon's base. Giant titanium pipes draw cold water from 400 meters deep, where temperatures remain a constant and reliable 12 degrees Celsius. This water is pumped through intricate heat exchangers, absorbing the massive heat flux generated by the core lithography machines. Heat exchange surfaces are treated with anti-biofouling coatings to prevent marine organism growth without using any harmful chemicals. Structural drones patrolling the perimeter utilize high-resolution thermal imaging to detect any microfissures in the steel hull. Each drone carries an automated repair module, applying military-grade anti-corrosion sealant to any identified weakness within seconds. Octagon's logistics are managed by a fleet of autonomous shuttle vessels that operate independently of human maritime pilots. These vessels use a specialized active stabilization deck to ensure delicate silicon wafers are never subjected to excessive G-forces during transit. A massive maglev transport spine moves finished chip modules to the packaging department at speeds exceeding 100 kilometers per hour. This supply chain is a closed-loop system where every byproduct is recycled or reprocessed to achieve zero-waste industrial output. Internal cleanroom integrity is constantly monitored by thousands of atmospheric sensors, checking for even the slightest pressure drop. Emergency graphene capacitor banks can sustain the entire factory's operation for 30 minutes in case of a sudden power failure. This redundancy ensures that the molecular-scale manufacturing process is never interrupted, protecting billions of dollars in active production. We are looking at the pinnacle of industrial autonomy, where human error has been engineered out of the equation entirely. Octagon proves that humanity can now manufacture at the limits of physics, even in the middle of the open ocean.